Let's look back at how we've been interacting with generative AI. For the last few years, the standard interface has been incredibly straightforward. You ask a question, and it gives you an answer. But until you typed that prompt, the system sat there, idle, waiting for instructions. That works well for writing an email or summarizing an article, but solving a complex problem, like developing new software or conducting empirical research, requires more than a single interaction. These processes take months of continuous testing, evaluating, and revising. This flowchart illustrates the distinct bottleneck this setup created. We had access to massive computational power, but a person still had to sit directly in the middle of the workflow. You had to evaluate every output, figure out the next logical step, and write a new prompt to keep the project moving. At Google I/O 2026, that structural limitation was addressed through a transition to an agentic model. Instead of a single model waiting for a human prompt, specialized AI agents are now designed to prompt each other. We are now deploying autonomous digital workforces capable of executing complex, multi-step projects from start to finish entirely on their own. To see exactly how these multi-agent systems operate in practice, we can look at software development. Google recently released Anti-Gravity 2.0, an environment specifically built to host multiple AI agents working in parallel. This network diagram shows what happens when an engineer uses the platform's teamwork command. They give a single high-level instruction to one primary orchestrator agent. That orchestrator immediately spins up dozens of specialized sub-agents. One agent writes the code, another runs a test, finds a bug, and sends it back to the first agent to fix. They cycle through this logic loop continuously, completely unguided.
During the I/O demonstration, this exact setup was asked to build a functional operating system from scratch. The autonomous agents handled every line of code, managing everything from the system scheduler to memory allocation. This level of automation allows a single developer to oversee high-level architecture, while agents handle the exhaustive manual implementation, significantly condensing the time required for major software builds. This same principle is being applied to formal scientific research. Google integrated these multi-agent workflows into a suite called Gemini for Science, which includes an AI collaborator named Co-Scientist. When researching a topic, Co-Scientist runs an idea tournament. Specialized agents pull data from millions of published papers, propose competing hypotheses, and actively debate each other to determine which theory holds the most promise. Once a strong hypothesis emerges, an execution engine called Empirical Research Assistance, or ERA, takes over. ERA acts as a specialized coder that writes the empirical software needed to physically test the theory. Instead of testing one model at a time, ERA generates and evaluates thousands of code variations simultaneously. It searches through these permutations, scoring each one in parallel until it finds a highly optimized solution. By automating the repetitive stages of the scientific method, AI is doing the actual legwork to catalyze breakthroughs across fields ranging from neuroscience to cosmology. These agents aren't confined to abstract mathematics or software architecture. They are actively processing messy, physical data to solve immediate problems. In clinical settings, an investigational agent called Symptom AI was recently tested on how well it reasons through complex medical conversations. In blind comparisons, independent clinicians preferred the AI's differential diagnoses about twice as often as those provided by other human doctors. We're also seeing this predictive reasoning applied to the chaotic physical systems of extreme weather. Google developed a forecasting model named WeatherNext to handle the massive, fluctuating variables of meteorology. This satellite image captures Hurricane Melissa approaching the coast. Forecasting rapid intensification is notoriously difficult, but the WeatherNext model successfully predicted the storm's spike in strength and its exact path with high confidence, 5 full days before landfall. That 5-day lead time allowed local meteorological services to alert the public well ahead of the surge. It provided the window of time necessary to secure vulnerable coastal infrastructure and evacuate residents safely. By applying deep reasoning to complex datasets, these systems have become vital instruments for protecting lives and securing physical infrastructure. To support hundreds of autonomous agents running continuous logic loops, the physical hardware powering these models had to evolve in tandem. Part of that evolution involves pushing computation directly to the edge. Google designed the Coral NPU and the new Coral board specifically to bring efficient machine learning directly to local sensors and physical devices. During the I/O pre-show, these edge processors were deployed at the Monterey Bay Aquarium. The local boards ran continuous object detection models to track the exact movements of live jellyfish, using that data to orchestrate a synchronized musical score. While the Coral board shrinks processing down to fit in a camera lens, Google's new Willow quantum chip is expanding centralized processing power far beyond the limits of classical computing. This chart compares processing speeds for the quantum echoes algorithm. The towering column is the time required by the world's fastest supercomputers. The barely visible sliver next to it is the Willow chip, executing the same algorithm 13,000 times faster, achieving verifiable quantum advantage. With this hardware scaling up to meet the demands of machine intelligence, our relationship with technology has shifted. We no longer spend months manually compiling code or running trial and error experiments. We are now managing teams of specialized digital researchers who handle the execution for us. As we integrate these autonomous digital teams into our workflows, the focus shifts from the mechanics of execution to the strategic direction of research.